and you know, we're working through it. But so we're going to improvise a little bit. Could I get a indication maybe in the chat? Somebody let me know if the audio is okay. I want to make sure that I can be heard. Yeah, great. Thanks, gang. Thanks, gang. Okay, well, so I'm in the back of the room here. Ron's going to be in the front. We've got some audio challenges here, and we're getting set up. So what we're going to do is we've got a great deck with all the tips and tricks of the tools that that all of you have seen in the press release. So we're super excited to talk about that. And then we're going to do some pretty cool hands-on stuff where we've got right here camera live feed with the XM2. We've got a Viavi 1X here. And we're going to do some things, create suckouts and go through the physics of that. So that'll be super fun. And with that said, I think we're about ready to get the introduction kicked off. Is that going to be me? Andy, can you start the presentation? All right, folks, it'll be just a minute. We're sorting the logistics here. Okay, this is a little tricky, you guys. So I'm going to be presenting from the back of the room. Ron's going to be presenting in person from the front of the room.
We got clickers, Larry. We're good.
Hey, I hear your audio, Andy.
I think we're ready to go. Hopefully, folks, virtually.
Yeah. Microphones are working? No, it's right here.
Oh, it's the laptop's picking it up?
Yes.
Yeah.
So stand next to the laptop and.
There we go. Okay. Excellent. We're doing what engineers do, right? We're improvising.
Yeah, we're going to improvise a little bit.
So, excellent. Thanks everybody for being here tonight. You don't know me, I'm Scott. Okay, I'm gonna get creative this through this. I'm gonna stand right here.
Okay, gang, I promise this is going to be fun. It's a little bumpy, but we haven't done this in a while. So
Go, okay. How we doing? You guys hear me okay?
much better. The closer you get, the better it sounds.
Right. Excellent, okay. Excellent. Well, very good. Well, thanks everybody for being here. Sorry about the minor technical difficulties. As you can imagine, we haven't done this in a little while, so we're running into a couple of bumps here and there. But as I mentioned, my name is Scott Miller. I'm work for Comcast, but I'm also a board member on Rocky Mountain SCTE's board. And we're happy to welcome so many faces here in person as well as online. So thanks for being here. And we've got some great speakers for you here tonight, and a little bit of hands-on for those of you here in the room. So thanks for being here. I'm just going to go through a couple of quick introductions, and then we'll kind of jump right into why you're here, because you're obviously not here for me. Okay. Well, SCTE. For those who don't know about SCTE, as you can see, I mean, we are a trade organization for the cable industry and focus on education and certifications and a variety of other things. As you can see, SCTE Rocky Mountain has won some awards over the last couple of years. We've spent a lot of time kind of trying to educate the community about the cable industry, reaching out to the community, doing community outreach, as well as getting folks certified and doing a variety of other things to help kind of spread the word of what the cable industry does. A lot of people don't truly know unless you're in the industry. If you're not a member of SCTE, we're more than welcome you to do so. If you're a member, if you work for companies like Comcast and Charter, it's actually a complimentary membership. Doesn't cost you a dime, but it gives you access to all kinds of resources, including continuing education and a variety of other things. Otherwise, you can go to SCTE's website. We actually, for those of you in person, we do have a link out in the lobby area there where you can sign up if you choose to do so and become an SCTE member. So certifications is one of the big things that SCTE focuses on for those of you that want to get certified in particular areas of the business. There's there's a lot of continuing education as well as tests that you can take in order to get those particular certifications. And there's a lot of literature here out in the lobby and as well that you're welcome to take with you on the different courses that are offered and things like that. Here's just a listing of kind of a few of the types of certifications that you can get. A variety here, just a sampling here. And let's just keep going here. So let's connect. So obviously we are connected on social media. So if those of you that don't know too much about us or you want to stay connected to Rocky Mountain SCTE or the SCTE National, because there are several chapters, dozens of chapters across the US. And you can connect with us individually off Facebook. We have a website that's got a whole host of information, Twitter site, and as well as there's a national website as well with a lot of information and continuing education that you can utilize. We did want to make sure that we thanked our sponsors. We have a variety of sponsors that allow this to happen. We appreciate the sponsorship of certainly Charter Communications as kind of our industry partner, but we have a variety of other sponsors that help to make sure that we can bring you these types of events every year, that we can continue to offer a variety of different resources for you here, especially in the Denver area, and make sure that that you're connected to everything that's kind of going on in the world of SCTE. So thank you to all of our sponsors here this year. And I guess with that, I'm going to introduce our speakers here for today. We've got Ron Hranac, industry professional, retired industry professional. They'll be joining us here today. Larry Wolcott, fellow with Comcast, and they're going to do a whole session here on tools that hopefully you'll find very interesting and informative. And for those, as I mentioned, for you in the room, you'll get to do a little bit of hands-on as well. So thanks everybody for being here or being online.
Hey, folks, we're going to try and be super cognizant of the microphone here.
Which is in the laptop
Which is
here.
in the laptop here. So we'll turn it up a little bit. Apologies to everybody in the room with the technical difficulties. We used to do this every last Thursday of every month for years. Our top participation for this event was 191 people in this very same room with Kate McNaught and the fiber splicing. It's just, that's like candy for cable people, right? Touching lasers and fusion splicers. So
My eye is still healing from that.
yes, yes. So this is our first gathering in a couple of years since COVID. So it's very exciting, but as you can see, it's a little bumpy with the technology. Please forgive us about the snafu with security and COVID screening and all that stuff. Any DNA tests you had to submit to get into the door, apologize for that. No, sadly, some of our colleagues were turned away because they didn't have their vax cards. We didn't really anticipate all that, so we apologize. And I will make sure we put a note out to everybody who couldn't be here. So that's one thing. We're behind, so let's get to the chops here. Ron, first of all, you've been introduced to us. Ron and I are old timers with, not as old as Ron, but with the chapter. We're very passionate about this. Ron has been a mentor and a friend of mine for many, many years, and we're just cable junkies. And we'll get straight away to the good stuff. Ron, next one. So P&M, this is proactive network maintenance. Here, Ron, why don't you pop into the talk a little bit.
People know what I look like, old cable guy. Proactive network maintenance has been around now for more than a dozen years. It got its start back in 2008 when Alberto Campos and some of his colleagues from Cable Labs presented a paper at SCTE's Cable Tech Expo proposing the idea of what is now called proactive network maintenance by enabling technicians to remotely identify and locate the presence of impairments in the field, and do so by looking at the adaptive pre-equalization coefficients in the upstream. That's part of the communications between the cable modem and the cable modem termination system in the head end. And the idea was that by looking at those pre-equalization coefficients, we could derive a frequency response signature from those coefficients, and then look for common signatures in neighborhoods or individual problems in drops. And from that proposal, Cable Labs started a proactive network maintenance working group in 2009. And here we are, more than a dozen years later, and P&M has been implemented by a number of cable operators. Comcast, of course, has implemented on a widespread basis. Charter implemented it, and a number of other operators also rolled it out. There are also third-party companies that provide software tools that are based upon a reference implementation that the Cable Labs P&M working group did several years ago. So this has become pretty widespread, and it is an incredibly powerful tool that has evolved since then to something that is now part of the DOCSIS 3.1 physical layer specifications. It's actually defined in the spec, and it is carried over into the DOCSIS 4.0 physical layer specification. So really cool technology.
And so getting to the nuts and bolts, why do you care about this? You either use, contribute to, support, maintain, develop
one of these tools or somehow it affects your life. These are all based on that very same technology that Ron was talking about. So spectrum analyzers in general are an approximation of what we can get out of the P&M stack. But Yeti, Spectra, the XM meters, Scout Flux, Noise Patrol, Parts of Watchtower, all these tools at Comcast that we know and love to do our jobs all day have in some shape or form been derived or
They're descendant of P&M.
descendants of
Yeah.
P&M originated from, right? That was the point. So we're going to take you through that. The fun part is we're going to go do some explanation, some pro tips and tricks from, from the experts. And I'm really looking forward to going deep and high and wide on a bunch of the different tools.
For those of you who use a different company's tools, you're not using Comcast tools, but maybe something at Charter, or you're using something from Brady Volt's company or from Aclisa, that's James Medlock's company, or other companies. The names may be different, but the capability is very, very similar. So we'll be focusing a lot on the Comcast version of this, but the concepts still apply across the board to the various tools, because all that information is based on data that we're getting from the CMTS in the head end or hub site and from the cable modems out in the field. And from that, we can take that data and do all kinds of really, really cool stuff with it. So we talked about this already, so we'll get past that and start with a discussion of spectrum analyzers. Question, how many in the room have used a spectrum analyzer? How many have used an HP 8591C? Okay, HP 8558B? That's going back.
They really old equipment.
All right, a spectrum analyzer is a pretty neat piece of test equipment that gives a display of the frequency domain. And what that means is that the display you see on the instrument is a display of amplitude or magnitude on the vertical axis and frequency on the horizontal axis. You can look at signals on a spectrum analyzer and really learn a lot about the character and quality of those signals and what's going on in your network. The neat thing is spectrum analysis has evolved far beyond the old 8558 and 8591C and Sunrise AT2500 and others to actually being built into a set-top box. Well, spectrum monitors probably a more accurate description of what's going on. I would have killed for, well, not really, but I would have killed to have that capability when I was a tech in the field back in the 70s. The ability to troubleshoot problems remotely using full band capture. How cool is that? That's something that we can do with this spectrum analyzer type technology. And the idea is that we're able to poll the modems and devices in the field and get data from those modems and create what looks like a spectrum analyzer display. And it makes it so much easier. And that's just another tool in the P&M tool set. And really what we're looking at is the power of the RF signal versus frequency. So we can do things like measure carrier to noise ratio, and we can see distortions, we can see the noise floor, we can see the signal itself, we can see a QAM A stack, and we can do all kinds of neat tricks and manipulate that over time. What we're looking at is RF. And I'd love to ask the question, what is RF? Well, that's what the abbreviation stands for. It stands for radio frequency. But what is RF?
Magnetic wave.
Well, it's electromagnetic waves. Yeah, this room is full of RF. It's full of they're photons. And you say, wait a minute, photons, that's light, isn't it? Well, yeah, light's photons. RF is photons. Gamma rays are photons. X-rays are photons. They're all photons. And even inside that piece of coaxial cable, we've got an alternating current. Yes, it is a form of AC propagating on the outer surface of the center conductor and the inside surface of the shield. And there's a field traveling through the dielectric, and that field comprises photons. And that the field has an electric field component and a magnetic field component. They're perpendicular to each other, and they're also perpendicular to the direction of propagation. But that's enough about what RF is. We don't have to understand all the physics behind it, but we do have to
A
understand.
picture says
cool
a
stuff.
1,000 words that Ron just said. Just look on the screen and there's what it actually looks like in a picture form.
And the analogy I love to do is throw a rock in a pond of water and look at the ripples.
Still,
You stole that from me. I've been using that analogy for decades. I was doing it before you were born. Come on now.
okay, so I'll take this one, Ron, because we actually have 52 slides and 48 minutes to go. So we're going to have to pick it up a little bit, Ron. So we're going to talk about the hidden spectrum. So what you're looking at in the frequency versus magnitude display, that's what a spectrum analyzer display looks like on the left. But underneath the hood, the adaptive pre-equalizers, that's what Ron was talking about with this PNM stuff. That's actually a vector sum where the phase and the amplitude are all basically put together and put on a flat screen. It's actually, remember, it's a spinning vector. So you can actually get a picture, a better orientation of spinning vector by separating the piece parts of it. So here you can see on the chart on the right, in our tools, this is called Flux. What we're actually doing is tuning a channel, demodulating it, and basically decoding the angle and speed and direction of those electrons. And that's what those graphs show you. Frequency, phase, and group delay variation are the discrete components of what the spectrum analyzer is showing, which is just more of an aggregate view of all that stuff. So I know it's pretty heady, but we're going to get into the details about how you interpret that and do important things for customers with that.
And the simple explanation of what's going on in adaptive equalization is that digital signals propagate through a channel, they get impaired, and the adaptive equalizer circuit, whether it's in the CMTS at the head end for the upstream or in the cable modem for the downstream, is looking at that signal. And it says, wait a minute, this signal's got, say, some tilt in it, 5 dB of tilt this way. So the adaptive equalizer digitally creates a filter with the opposite complex frequency response of 5 dB tilt the other way. And when you combine the two, the channel's nice and flat. So those coefficients are complex numbers that describe how to create that filter. And from that, we can create a graph that shows us the frequency response of the channel.
There you go.
Now, this is modulation. Oh, modulation is cool. We use this in the world of RF and in the world of light, but particularly in the world of RF. If we want to convey information, how do we do it? Well, to do it over RF, we can vary one or more characteristics of the RF signal to represent the information. We can vary the amplitude of the signal from RF signal. We can vary the frequency of the signal. We can vary the phase of the signal or some combination of those. An example of amplitude modulation, their favorite AM radio station that maybe you listen to a football game on. FM, that's frequency modulation where the frequency of the signal varies. And a good example there is your favorite FM station playing the music that you like to listen to. Phase modulation, that tends to get into the world of data. But in the case of our single carrier QAM signals in our cable network, those use a combination of amplitude and phase modulation. So we're varying the amplitude of the signal, the RF signal, and the phase of the signal to represent the ones and zeros that we want to send through the network.
This slide shows it really well, right? So this is actually in one of the patents in the technology. I took the word Comcast, and this is how the modulation works, right? So somewhere is a pattern of bits that represents the letter C, O, M, C, A, S, T. And think about that as a dartboard. And we're trying to very precisely aim that beam of electrons to scatter across that dartboard very fast, is at the rate of symbol period. And so those things basically splat against the dartboard, get peeled off and converted into whatever it is that we're trying. I mean, there's a lot more in the lower layers to get to the decoding into the actual words, but fundamentally that's how it works, right? And the further or the more accurately we can hit those darts in our dartboard, the more precise and fast and awesome our service is.
I want to go back just a quick second on this slide. I suppose most of you have probably seen a constellation display like you see on the right side of the screen. You ever wonder what that's showing you? If you think about it from the perspective of the amplitude and phase of the RF signal, that is essentially a graph of the instantaneous phase and amplitude of the signal. So if we think over here on the far right side of this from the center over to here is 0 degrees relative phase. And then as you go around in an angle, you go 360 degrees. So that dot in the upper right-hand corner would represent an RF signal that has maximum amplitude, because it's all the way into the corner, and it has a relative phase of 45 degrees. So in reality, the RF signal's amplitude and phase are varying continuously, but the receiver is taking a snapshot of the instantaneous phase and amplitude in time, and assuming the timing lines up, then we can plot it on a constellation graph like this. So that graph is essentially showing us the instantaneous amplitude and phase of the signal. And each combination of amplitude and phase represents a group of ones and zeros that we call a symbol.
This is basically what you just said in picture form.
Well, the neat thing about this is we can look at that constellation display and characterize certain impairments to the signal. Ideal one on the left. The instantaneous phase and amplitude is exactly where it's supposed to be when it takes the snapshot. But the reality is the RF signal mixes with noise. There can be phase variations if there's a problem with the transmitter or the receiver. You can have compression if you overdrive an amplifier or a laser and clip the signal. So you see those examples of impairments all over the screen here. Ideal on the far left. The next one would be a case where the carrier to noise ratio is low. So you see the RF signal mixing with the noise. Well, the receiver doesn't know the difference between the noise and the RF signal at a point in time. It just plots it at that point in time. So it spreads out those constellation points and we get the fuzzy dots. The next one is an example of compression. And then the last one is an example of phase where it looks like the constellation display is trying to rotate. So you can think of the constellation display as a way to show what's going on.
Does anybody in the room use regularly an XM1 or XM2 meter? Anyone? Couple folks. If you tune a Laka CW, that's what it looks like. So,
All right.
okay, we're gonna get to Yeti. This is one of my favorite tools. And so who in here has ever, still does, or remembers Path Track? Right on. Who wants to go back? Okay, no, don't even try it. Don't do it. Okay, so Yeti is one of these P&M things where we figured out, hey, you know what? The DOCSIS chips are doing this stuff anyway. If we can figure out a way to extract it and by way of Cable Labs and all these other venues, get it into the specification, go to Broadcom, have the CMTS vendors do it, instead of having a separate piece of equipment sticking in the head ends that's split and measuring and watching copies of the RF, we can actually ask the CMTS, tell us what you see. That's what Yeti does. And it basically takes the upstream RF spectrum from the burst receiver, and it basically does all of the fancy FFTs and gives it back to our tool. So now that we don't need all of these things, we can see the same thing as humans that the CMTS sees. And the interesting thing about doing it that way is we also have knowledge of what the CMTS has knowledge of. How well is the signal working? Meaning, what's the MER of the channel at the time? So now I don't have to have a picture of the channel and then another tool that shows me what's the performance of the channel. It's all in one pane of glass. So it's pretty neat that we can connect to the CMTS, do the traditional spectrum analysis as humans, and then see the effect statistics, the MER, a lot of other great stuff. Now, if you're troubleshooting upstream noise, you're probably in network maintenance, or all technicians eventually run into upstream noise. But in terms of the field troubleshooting process, this is where it's especially useful. And let's see here. We'll talk a little bit about some of the tricks and tips of Yeti. If you use this all day, you're probably aware of some, but I'll probably talk about a couple that aren't. So go ahead and flip it around. So this is where I talked about having that knowledge of communicating to the CMTS and say, not only give us a picture of it, but tell us what you see. We can also, through software, and you can't do this with PathTrack because it's two completely disconnected systems. I have a picture of the RF here, and then I might have another tool showing me what the performance actually is. This puts them all into one converged pane of glass. And here you can see, because we have that shared knowledge in one tool, we can actually colorize things. We can make recommendations and say, this is an XB3 CMD noise hump, all this other stuff, right? And so it's really powerful in that we can integrate the other performance metrics into one place. So it makes the interpretation, meaning you as a human looking at it and figuring out what to do about it, a lot easier. Can you hit the next one?
I've got a question for the folks in the room though. As you look at the plum haystacks across here, you see that the one on the far right is taller than the others. Is that the way it's supposed to be? And I'll let you think about that. Carry on. We'll come back to that.
All right.
We'll come back to that.
So this is in the tips and tricks category. So first off, there's this thing called quiet time. You cannot do this with PathTrack. So for all of those who would say, I want it back, remember this one. The CMTS knows when the cable modems are supposed to be talking and bursting. The CMTS also knows when they're not supposed to be talking. So Yeti has the unique capability of saying, CMTS, grab the spectrum and show me the picture when everybody's not talking. The reason that's super important is because the noise and things that are interfering with your signal aren't scheduled. They're showing up when nobody's talking and when people are talking. So from the troubleshooting perspective, if you're trying to see, hey, what's interfering with my signals, you can effectively make your signals invisible by going quiet time mode, and you can now see the noise environment that's hitting the burst receiver. So just tips and tricks, super useful. Quiet time, of course, if you use the tool, you already know that. But I will tell you, it has the kind of this heat map view that's killer. On the bottom, you'll see it circled with the half-life in the end-tile sliders. It's very, very helpful for seeing accumulation of noise in certain frequency spectrums that normally you have to know all these different crazy things to do it in the old tool, zero span and whatever like that. So very, very useful for visualizing different types of problems. Turn the quiet time on, tweak with the half-life and the end-tile, and you'll start to see the heat map tell you really interesting things about the performance.
Now, I want to go back to that question I asked. That narrower bandwidth QAM signal had a higher displayed amplitude on the screen than the wider bandwidth ones. Is that correct? Or does that indicate a problem? Any guesses? Well, the answer is it's correct. And the reason is that the cable modem and CMTS are configured for something called constant power per carrier, which means that when the cable modems are transmitting in the upstream and the signals are received at the CMTS, every QAM signal, regardless of its bandwidth, has the same power. You say, well, wait a minute, that narrow bandwidth one is taller. Well, yes, it is on the display, but it has the same power in that narrower bandwidth that a wider 6.4 megahertz bandwidth ST QAM signal does. The wider the bandwidth of that signal, the lower the height on a spectrum analyzer display for a constant power. The narrower bandwidth signal will be taller on the display. It has the same power. So for every time you double the bandwidth of the QAM haystack, the height changes 3 dB. So if that's a 1.6 megahertz wide haystack compared to a 6.4 megahertz wide haystack, the narrow one's going to be 6 dB taller than the other one, assuming they have the same power. There's the answer to the question.
All right, so we're going to move on. Yeah, the full band capture, that's the ability for cable modems to basically provide the spectrum analysis, that we've been talking about remotely. And at Comcast, we're among friends here, we're about 50 million cable modems, CPE, that have embedded DOCSIS cable modems in it, set-top boxes, etc. The total population that is now capable of doing this kind of reporting is upwards of 45 million. So it's a vast majority of our population. And think about before we had this, the process of troubleshooting the cable plant was different, right? You had a spectrum analyzer, you had a PM maintenance schedule maybe, or you would respond to trouble calls, or you see clusters of red dots maybe, and you go start to take measurements to figure out where the problem begins, where the problem ends. But now the tools, because we are at the end of virtually every line doing those same measurements, it allows the tools to automate and show you clusters of things like resonant peaks and suckouts and standing waves. And you can focus more on where do I go to start fixing the problem rather than let me go to the end of the line and start troubleshooting and isolating, which is incredibly time consuming. So also the name Spectra is our Comcast name for one of our tools that does the aggregation. It's the plural form of Spectrum, which was fitting, and it sounds kind of like a superhero, so we just thought we'd call it that.
But it uses full band capture, which is built into the silicon in the cable modem. So you've got essentially 45 million spectrum analyzers in homes and in the network. That's pretty cool. That's just in Comcast. Think of all the other cable operators who've got full band capture capable cable modems out there. That's spectrum analyzers in almost every home, or at least every home that's got a capable device.
And what would we do if we had that, Ron?
Hey,
Okay.
water in the drop.
He's not here today, but so we're going to go through. We actually published, if you're curious, a new industry reference document. Ron and I are on the network operations subcommittee. It's called Industry Reference 280. It basically, in layman's terms, describes everything that can go wrong with cable RF spectrum in the downstream. And it not only shows you pictures, this is an example of that, but it tells you what to do about it, right? Which is pretty cool. And so interesting industry reference 280 SCTE, if you're curious.
If you go to SCTE's website, scte.org, go to the standards download page and look for SCTE 280-2022.
To be precise. So in this case, he's not here today. I thought maybe he would be here, but Jeff Milkoch was with us. He's runs Mountain West maintenance, or at least Denver, I don't know, but this was actually Jeff on the very first trials a couple of years ago where we figured out what this signature was. This jagged frequency response, well documented, turns out water in the cable. And water has very unique physics with electrons, and it causes frequency specific attenuation and other things. And we won't spend a lot of time because we don't have it. After we fixed it is what it looks like on the bottom. When we detected the water, it's on the top. And this is all automatic now. Our tools can tell us when we have water in the cable, which is pretty incredible.
That water in the cable creates a very unique signature. And as you look at that, you can see up here that it slopes from low frequency to high frequency. And you have a non-periodic waveform, if you will, or ripple in the display. And it's very characteristic of water in the drop. And if water gets into the dielectric, it changes the dielectric constant, which changes the velocity of propagation, which changes the attenuation. And since it's the water can be who knows where in the cable, it can cause all kinds of suckouts like you see up here. And it's definitely something that when you see that, replace the drop. You don't cut the connector off and
Don't do it.
cut
Don't
back.
drain it. Just replace it.
No, replace the drop from the tap to the side of the house. But and this is cool. You can see this remotely without going to the customer's house. See, I know what that is. That's water in the drop. And go out and replace the drop.
Another signature that's described in this 280 is high frequency roll off. And this is again a side effect of water, but it's slightly different. It's not spread over the length of a coaxial cable and ingressed into the dielectric, creating pockets of frequency specific non-periodic attenuation, as Ron would have said. However, it is pooling up and causing high frequency roll off. It is frequency specific, but it's not periodic. And you'll see this shoulder effect. And it's the difference between a filter roll off, like if you're trying to use higher frequency than you have in one of your filters. Filter roll offs really look round and perfect. High frequency water roll off is usually very abrupt and kind of terse like that. Talk about the famous pullout, Ron.
Oh yes, the pullout. In this happens in a couple instances. One is when it gets really cold. The cable physically contracts in length and it can pull the coax out of the hardline connector. I have seen examples where it got so cold, and this would primarily be, say, in Alaska or parts of Canada where it gets real cold, where it'll actually break the housing and pull the connector and the 5/8 24 port entry and physically break the housing and pull it out of the amplifier or the tap or whatever. And in this case, what you see is low frequency roll off when it pulls out. Because in this case, we're losing continuity between the center conductor of the cable and the center conductor seizure mechanism, in this example, in the connector, as well as the shield. And so that causes attenuation at lower frequencies. And you see this low frequency roll off, and gee, when you fix it, it looks really good, like you see circled in the green here.
Right, so we have water signatures. It's a really unique jagged signature, right? You'll all recognize that for the rest of your days. It's pretty scary looking. High frequency roll off, low frequency roll off. Pop quiz, Ty, what causes high frequency roll off? Yeah, the previous slide. Water in the tap. Yep, see?
Or water in something, yeah.
Perfect. Pop quiz, Andy, what causes the jagged signature on the frequency spectrum? Water, you're right, perfect.
And what causes low end roll off?
Low frequency roll off, anyone? Separation of the shielding, yeah.
And the center conductor. You might also see that with a loose center conductor seizure screw.
Yeah, yeah.
You can see that.
So you're all experts. Welcome to the club. Oh, degrees? I thought you were talking about relative power.
Well, and part of the problem could be the way the plant was built.
Yeah,
A lot of times the contract, and I suspect a lot of this art has been lost. And that is building the proper amount of sag in the spans between poles and having proper expansion loops in combination with the proper amount of sag to take up the expansion and contraction of the cable, which is different than the contraction and expansion of the strand. And if you have that, you can usually avoid this problem. My guess is that span was probably tight as a guitar string during the day, 60, 70 degrees. And when it got cold, there was no way to take up that contraction. They just pulled it out of the connector.
hold on. So all of you guys out there, we're gonna speed it up. We're on slide 17 out of 52, so we gotta get moving, Ron. Let's turbo mode through these slides. Okay, this is the resonant peak. 3-sentence explanation, Ron.
3-sentence explanation typically occurs with bad grounding, loose screws, bad solder connections, and so on inside of an active device most of the time. Could be a corroded connector or something else, and pull the module out, put it back in,
Tighten everything up.
properly, and it usually fixes it.
What's the most common repair activity to solve this in the field? Anyone? Hannah, what would you do to fix this? Be honest. Don't lie. Kick the pedestal.
Kick the pedestal.
Or whack it with a stick. I mean, you're trying to impart vibration onto the enclosure so that you can basically.
What is effectively happening here is oscillation. You've all been in an auditorium where somebody gets a microphone too close to the speaker, turns the amplifier into an oscillator. Same thing happens here. We're getting feedback through that bad grounding path into the RF stages, and it creates the equivalent of RF feedback or oscillation, and it shows up as this resonant peak.
And please don't kick pedestals, right?
Yeah,
Pull it out, put it on,
Don't
torque
kick
everything.
pedestals. Take it out, put it back. If the
And then it
module's
won't come back.
If the module's got cold solder joints or something, then you'll have to replace it. But the question is, how do you get water in the drop? Water can get in the drop through an F connector that is not properly weatherproofed at the tap, for example. It can get in the drop through squirrel damage to the jacket of the drop cable, where the drop rubs against a tree limb. Any kind of abrasion or cut on the jacket will let water get in, and it will eventually migrate through the length of the drop.
Yeah, and I'll tell you, one of the most common things that we found with this water detection is more just a little nicks in the jacket, not even a chew through the shielding. Like if you tear the messenger wire too fast, you can put a tear in the jacket. Just that little tear with water running down every time it rains, it soaks in like a sponge. So you got to be super cautious, like little knife marks, tool marks, anything. Very, very cautious.
Is this a company now or it's always been a problem?
Always been a problem.
Always been a problem.
Water and drops
This
especially.
full band capture lets you see what the signature looks like, and you can identify it remotely and say, that customer's got water in the drop. Get somebody out to that address, replace the drop.
Yeah, and so let me give you a picture about what we're doing right now in the tools. So that signature group here, that's your resonant peak, right? That's caused by an amplifier. This particular signature is a specific amplifier, and it's 100% accurate. Like there's only one thing that causes that signature. Now the tools are getting smart enough. If you look at this is Watchtower. This is what all of the symptoms of the problem are: FEC, MER, wobble, and channel plant fault. Those are all caused by this one thing. The new tools are getting smart enough to say, we see all these symptoms. This is the picture of the spectrum. We can join that to the map and tell you which amplifier. So we're going to push that to the side and very simply say, go to this amplifier, inspect the module. Right? Like talking about making your life a lot easier. When you see 200 events from symptoms of a problem that you haven't put together in your head, which is hard, the new generation of the tools is really going to be powerful. Yeah, this is an example of what we talked about. Here's your connectors, and generally picking it up, reseating it kind of clears.
You gotta face the.
Oh, yeah, sorry, clears the corrosion interfaces that happen on those connectors. And then, of course, you'll have loose screws and things like that. Any one of these.
But in this example, it's caused by a little bit of corrosion at the connector interface between the module and the motherboard in the amplifier. So you pull it out, put it back in, tighten everything properly, close up the housing, tighten it properly, and that should take care of the problem.
And not come back for a reasonable amount of time, couple of years.
Yeah.
So we're gonna quickly, this is our hands-on part. So our XM1 and XM2, all that cool software that we just talked about, like Flux and Spectra and all this. When DOCSIS 3.1 came out, we realized we have the software capabilities in-house to do all this analysis. And I remember Tony Warner came down with John Heslop and he said, you guys, these meters are hugely expensive. Every time we do a new version of DOCSIS, we can't go buy a new meter. So we got to figure out a way to take that software and come up with your own meter. So that was really, it started right here at 183 Inverness, the XM1 and the XM2. So we do our own field meters. The team is actually around the world now, but basically started here and a lot of the folks are here in Denver, in this building even. So it's pretty cool. Very proud of that. We have 25,000 of our own meters out there running around the country right now, which is pretty neat. Pros and cons, of course, there's lots of different meters, but we'll get to that in a little bit. We're running short on time and still have plenty of slides, so we're going to fly. This was, I'll talk a little bit about this. Who had an XM1 in their lifetime? Right? Who had an XM1 with a broken barrel on it? Okay, well, there's your repair crew. That's my boys. At 1401 Wynkoop, we actually had Bring Your Kids to Work Day, and we had everybody's kids soldering barrels for us. I'm not kidding. It's true. It's true, but it was really more for fun and learning, not really as a warranty.
Not indentured servitude here.
It wasn't free. I paid them in candy, as you can see. So just kidding about that. That's fun. But there's a lot of widgets because we control the software. Whoa, all that power that we showed you in the tools you can do remotely, you can also do mobilely. You can carry it around and go up into a bucket and go take a measurement at a tap. You can crawl into the attic where it's 120 degrees and do it all without the benefit of air conditioning. So we've got all kinds of neat functions, not a lot of time, so I won't deep dive into that until we get to something more interesting. Downstream Spectrum is the XM2, well, both of them, the XM version of the Spectrum Analyzer. But it also has the ability to use the tuners built into the meter, just like the set tops and the cable modems. It's really a DOCSIS cable modem chip inside the meter. So anything the cable modem can do, the meter can do, but even better. I want to talk a little bit about the automation of how do you interpret that, right? Like there's a lot going on with the Spectra. We showed you water waves. We showed you high frequency roll off, low frequency roll off. There's about 15 of them actually. And if you go look at IR280, you'll become an expert at all of them. But the tool actually does some of that for you. The very early version that we embedded onto the meter does some limited wave detection, suckouts, and all of that. It's not awesome, but it works. And that's part of the software that was actually started here at 183 Inverness.
And the idea is that it's taking advantage of the full band capture functionality in there, and then it can use signature identification algorithms to look at that. Because we can look at these with our eyeballs and say, all right, we've got amplitude ripple, we've got a suck out, we've got roll off. You can teach software to identify those things too, which helps speed up the troubleshooting.
Yep. And this is really a unique problem for the meters, is that the pre-equalizer response actually requires you to be a DOCSIS cable modem because it's part of the DOCSIS conversation. And every 20 seconds, this thing occurs where they're synchronizing and correcting for plant problems and problems in the wiring and the frequency response, and correcting it. The problem is once it gets corrected, if you're looking at a spectrum analyzer, you're looking at a picture that's been obscured from you, because what it does is it actually fixes the problem so that by the time it gets to your spectrum analyzer, you don't see the problem. That's where this hidden spectrum comes into play. Ron, talk about QAM analysis.
So we touched on this briefly a little bit ago, but by looking at the Constellation display for an SC QAM signal, you can troubleshoot all kinds of things. You can, as we showed earlier, you can see things like the impact of low carrier to noise ratio or phase noise or compression or clipping of the signal. And the neat thing is that by understanding what a Constellation display looks like, you can figure out the types of, some of the problems that are affecting the SCQAM signal. Now, they don't tell you necessarily why the carrier to noise ratio is low, but it can tell you that it is low and it's affecting the data. And as you look at the Constellation display, pretty soon you start to correlate what you see on the Constellation display with reported parameters such as MER, or modulation error ratio. And I like to explain that MER is essentially a measure of how fuzzy each spot in the Constellation display is. The fuzzier or more spread out it is, the lower the MER. The smaller each constellation point, or the tighter it is, the higher the MER, and you want high MER. That would be ideal on the upper left. Of course, you're rarely going to see that in the field. You're going to see at least the effects of noise in the cable network and the optical fiber links, so it's going to spread out those constellation points. And remember, each one of those points represents a symbol, which is a group of ones and zeros. Oh, then we get into OFDM, orthogonal frequency division multiplexing. This is not a new technology, but it's new, well, relatively speaking, to the cable industry, because we haven't used it before. But it's been used in Wi-Fi and LTE and all kinds of things for a long time. It's just that when DOCSIS 3.1 was introduced, it brought with it this thing called OFDM. And with OFDM, we're not limited to 6 megahertz wide channels anymore. The neat thing is that an OFDM signal is made up of a whole bunch, and when I say whole bunch, several thousand little tiny QAM signals that we call subcarriers, and they actually overlap each other. You say, wait a minute, how can a QAM signal overlap another one? Won't that cause interference? It won't, because they're orthogonal to each other. And that means that they don't they're mathematically related such that they don't interfere with each other. And we can have a channel anywhere in the downstream from 24 megahertz wide up to 192 megahertz wide for one OFDM channel. So we're not limited to these 6 megahertz channels anymore. And that, along with that, DOCSIS 3.1 brought us some much higher modulation orders. And those modulation orders go far beyond the 64 QAM and 256 QAM that we've been using for many years, all the way up to 4096 QAM or 1024 QAM. And in the future, how about 16,384 QAM? What that means is way more data, but in order to get it, we've got to have much more powerful forward error correction. And along with OFDM, which is a really nice way to get more spectrum efficiency in the network, the forward error correction, or LDPC, makes it a lot more robust than the Reed-Solomon error correction of our traditional QAM signals.
All right, well, folks, we're coming up a couple minutes short of our hour mark. We're on schedule to go to 5:30 with some hands-on, but we're going to move hyper fast through the last 30 slides. I'm just kidding. We have about 10 slides left, and I'm going to just cover these. These are Comcast tool specific, so I'll go very fast on these, and we'll get to some of the fun stuff. And we actually have a camera with a live feed to the web stream about the impairments, and we're going to do show you guys how to create suckouts and how to interpret it, and shorts versus opens, and it's going to be pretty neat. So bear with us here. We're making up for about 10 minutes of lost time with technical difficulties. The tools are very good for detecting noise in Ingress. This is when things get in that aren't supposed to be there, they cause interference with our signals that are supposed to be there. And when things like squirrel chews and loose connectors and damaged cables, when that shielding integrity becomes compromised, these other things get in, and then our modulation, our signal that we're trying to bring to our customers becomes compromised and performs less, just to very simply put it. Impedance is not something we're going to go talk about this minute, but just know that 75 ohms is good. Our cable systems are designed to run at 75 ohms impedance. And when they're not, what happens is some of the energy reflects back. And that's how all of these things actually work, is we can actually measure the reflected energy and say how far away it is and how strong it is and all this other stuff. That's really what Scout Flux does for any of those of you who are Comcasters and use those tools regularly. That's measuring impedance mismatches and doing a lot of fancy stuff. Pre-Equalization Basics, we were a little bit out of order, but that was what Ron was talking about, where we are able to perceive the problems in the plant basically pre-distort it in the other direction and shove it through the bad plant. And by the time it makes it through the impairment, it's actually nice and flat. It's
And that's in
really
the upstream.
in the upstream. It's actually
Slightly different process in the downstream.
incredibly brilliant and it works great for us. This is a quick look at what that looks like. So obviously where the problem starts and the problem begins is where you see that red is bad and not red is good. So interpreting that is a little bit of an art form. We're going to show you this hands-on in just a few minutes here with open circuit versus short circuit and how the phase response looks. So we've got a glass of salt water and we'll cut some ends off and short it out and do some neat things and give you an example of that. So I won't kill it here. But in order to do all the signal processing, it's all done digitally through fast Fourier transformation. And this is where the land of time and frequency and space and time converge. Describe.
How many of you have played with an oscilloscope before? And then how many of you played with a spectrum analyzer? How many of you have looked at the same signal on an oscilloscope and a spectrum analyzer? You can see the same signal, but they look a whole lot different. The oscilloscope shows amplitude versus time. Spectrum analyzer shows amplitude versus frequency. Yes, and mathematically, you can convert between those two domains using Fourier.
And it's a little wacky, not trying to blow you out with the Fourier formula, except if you look at the graphic, it's the same signal, you're just looking at it a little bit differently. Think about looking at a hose when the water's coming at you or looking at a hose when the water's going by you. It's time versus frequency. The way that we actually interpret that is we can match the signatures using some pretty interesting math, and it's really accurate. So we can say pieces of this signature or signal match pieces of that signal, and therefore they must be common to this network equipment. Short circuit versus open circuit is what we're going to talk about. Do this hands-on. I have exactly these exact same tools from 10 years ago in the back of the room. We're going to bring them back to life. Ron, talk about how open circuit and short circuit work.
Let me ask the question, how many of you have used a time domain reflectometer to troubleshoot plants in the coax? Not an OTDR, I mean, the function is similar, but a metallic TDR to troubleshoot coax problems. Okay, there's some pretty cool things that happen. If you've got an open circuit versus a short circuit at the end of a transmission line, what happens to the incident signal as it hits that and then reflects some of the incident signal back? For an open circuit, the reflected voltage is in phase, and for a short circuit, the reflected voltage is out of phase from the incident signal. And you may remember that on a TDR by seeing the trace showing the beginning of the TDR, where the TDR is located through a length of cable, and then it went up like this at the end. That indicated something that looked like an open circuit versus down that looked like a short circuit. And if you look at different traces and signatures on a TDR, it's also showing you things that are kind of in between ideal and a true open or a true short circuit. Yeah, and here you see ideally flat frequency response. And when I say frequency response, I'm talking complex frequency response, which includes magnitude and phase. And that's a piece that we often don't see, is the phase component.
And so why do we care about that? That's weird. Who cares about open circuit, short circuit? Well, if you're out there troubleshooting like Hannah, and your job is to figure out what do I have to fix on this cable, knowing that it's an open circuit fault versus a short circuit fault can be night and day, right? If Hannah, what causes open circuit shorts on or faults on a hard line? Give us any example. Open circuit, yeah. What kind of reflection would cause it? Open circuit problem. Radial crack, perfect. What else? Yeah, exactly. And troubleshoot, if you know it's an open circuit short, you know what to look for. What causes short circuit reflections anyway?
We'll look through the cable.
Yeah. Shovel digs in yards all the time. Dogs. Cuts.
Yeah.
If
Yeah, you get a cut. If the cut can give you an open circuit or a short circuit if the shield makes contact with the center conductor.
So that's super important for troubleshooting. Forget about the gory details. Here's my version of the pond metaphor, Ron, that you stole from me.
Get out of here.
Here's the proof that really think about it this way. If you have a perfectly clear pond and you throw a rock into the pond and it creates ripples. If you know the temperature and the surface tension coefficient of the water, and basically that's it. And you can very precisely measure the frequency separation of the ripple and the magnitude of the ripple. You can collectively use that all information to tell exactly how far away and how big the rock was. Like it's a reverse engineering process, but they're all very well related. That's kind of profound, isn't it? So when we see a standing wave in our plant, and you'll see those here, we're doing exactly the same thing. We know how fast our electrons travel. We know what frequency they're at, and we can very precisely measure the amplitude and the amplitude separation and the magnitude. So with all of those factors, we can now very accurately say how big the problem is, how far along the cable, what kind of cable, etc.
And neat little side trick, the water ripple analogy, which I've been using for decades, way before I knew Larry, can give you a really good analogy of RF through the air and helping to understand frequency and amplitude and wavelength. So throw a rock in the water, put a stick in the mud, and count the number of ripples that go by that stick each second. There's your frequency.
Stick in the mud is right.
That's right.
Okay,
and
so
I'm proud of it.
so
Fossilized mud.
So to give you an example, this is our tool. This is our Scout Flux tool. What do you see there? Ripples, right? Well, 5.12 megahertz bandwidth.
That's the symbol rate bandwidth.
The symbol bandwidth of that channel. Now we can look how precisely within fractions of a megahertz, I can actually measure the peaks of those separations and the magnitude. This is how Flux works, and this is how the ETDR works, and this is how open and short works. So you just learned something. Hopefully, next time you look at the tools and like, what does that mean? You'll know, oh, that is really a proxy for me to understand what distance is. And on cable, time and distance really mean the same thing.
And you know the shortcut for looking at the ripple to tell the approximate distance between two impedance mismatches? If you've got a 6.4 megahertz wide QAM signal in the upstream with the 5.12 megasymbol per second symbol rate, then each one of those taps or vertical red bars is equal to about 85 feet of distance in the cable, assuming 87% velocity propagation. You see 3 of those ripples, 3 times 85 feet. 255 feet is the distance between 2 impedance mismatches. That's called a 3T echo.
No kidding. So if you see all of these on one common piece of cable, you start at either side of it. Here's the part that we don't really know which side is it you walk from. You walk 255 feet and you're going to get really close to the phone. Yeah, that's how it works. It's pretty cool stuff. And so a little bit about that. We'll skip the parabolic interpolation.
Just a way to make the numbers a little bit more accurate.
Yeah, we fudge them a little bit, but there's some math stuff that happens in here. Noise patrol. So we're over time. This is a neat view of this cable modem spectrum analysis. What is this stuff in here? Anybody, quickly? Noise, yeah, noise is bad for cable. Like that's noise. This is actually FM noise. You can see it's
He's pointing at FM Ingress for the people.
pointing at FM Ingress. Noise is bad, so that's what Noise Patrol's job is, to help find all that stuff for you. We're gonna skip this. So this is it. This is the end of the presentation. We do have this great hands-on where we're actually going to do some of this in real time. We apologize. We actually hit just an hour with a little bit of rushing. Sorry about that with the technical difficulties. But for those of you who are out on the web and on the stream, we're going to patch the camera in and it might take a couple of minutes or so please do bear with us. But we're going to have some fun and we'll be joking and hopefully find a way to get the audio in as well. So bear with us and I really appreciate you all. Okay, so what we're going to do is take you through some impairments. And in this case, we're going to intentionally create a very large microflexion. So we'll almost call it a macroflexion. And here you can see, let's see if we can upload the video. Right now we're connected using a really nasty Radio Shack splitter, but inside of the splitter it has some circuitry. These are, we're going to replace that with a T. This T has none of that important circuitry in there. It's basically a power divider. So you would think, well, isn't that just what a splitter is? Technically, the T is a splitter, but it divides the power rather than splitting it, and it also divides the impedance. So each end of this of this T is 35 ohms apiece rather than 75. That's the answer. So I'm going to do a little oops, look at this. All right, so there's our live spectrum. Now you can see it's disconnected. And lo and behold, when we hook up our, there we go. Now, you see that nasty standing wave in there? That is actually a reflection coming off of, actually several reflections. There's a reflection coming off of the jumper because, like I said, this thing is not 75 ohms. It's half of that. Now what I'm going to do is take a very long drop cable and connect it to the other side. And let me stand by here. Got a couple of different things going on. Yeah, so there's actually two reflections in here. I didn't think about that one. This oops, set the spectrum capture. Okay, there's a standing wave because of our impedance mismatch here. This T is. Now, what Ron is going to do is he's actually going to start cutting this really long drop cable that we have to start basically shortening the length of the micro reflection. Yeah, keep cutting by 10 foot long. You know, the problem is, Ron, that this micro reflection is actually stronger than this one. Yeah, so you're going to have to basically go to 20 feet and cut from there. So I just start this way. Okay, so Ron is, let's see if I can get a picture. Ron's over here with a wire cutter. He's going to start snipping. It's still way too long. Okay, so Ron is going to let's go shorter than that. Oh, my God. Let's reconfigure this a little bit.
Attenuator pad.
Yeah, that would do the trick, but I do not have a pad here. We're having technical difficulties.
Anybody have 60 pad?
No. So why don't you go ahead and cut it some more, Rod? I don't think it's going to matter. It doesn't matter. This reflection.
That may be bad. Try the other one.
Oh, yeah. Okay, so Rod took the good ones. I'll keep an eye on this guy. Let's try this. There we go. Okay, everybody see that spectrum?
Bad T.
Yeah, we actually, believe it or not, the 1772. We just there's a party of people on. So here, what we're going to do, folks, is I'm going to reset this, and we're going to now introduce an exceptionally gnarly micro-reflection. There you go. Okay, there's what we call a standing wave. So I'm going to reset this this peak hold. Okay, that's the effect we were trying to get. So for those of you who are actually watching this and paying attention, nobody in the room is, we're having fun socializing. But that is what we call a standing wave. And so now I'll have you watch Ron. Ron is going to continue cutting. Oops. Hold on, Ron, if the display stopped reading. Oopsie. Hold on, we're having technical difficulties here. Let's go on from Spectra. Hold on, folks. We know the technical difficulties. The demo gods are not with us today. There's a spectrum. Okay, back to the demo. So there, folks, is what we call a standing wave. And if you remember what we talked about, and do the math, 492 feet per microsecond times 0.85 for the velocity of propagation of this cable. And Ron, as you can see here, let's show everybody what you're doing. Ron is going to cut the cable. He's going to cut the cable. Keep your eye on that standing wave. Okay, now you can see the old standing wave in the blue. That was the average that it measured. And now compared to the new standing wave that changed. So I'm going to go ahead and reset the capture. See, it's getting wider. See how our standing wave separation peak to peak and melting is getting wider? That's because Ron is cutting the cable shorter and shorter. And so I'm going to refresh this. Now you can start to see the periodicity, oopsie, is getting wider and wider against standing wave as Ron cuts the cable shorter and shorter. So sooner or later, you can see it's getting much wider, and you can see the frequency separation here. I don't want to see it counting it, but right now, how much distance is on this cable?
This length is like 4 feet.
4 feet. Yeah, that's about a 4 foot microflexion. So why don't you cut that in half? Try to go right in the middle. Now Ron just cut that 4 foot unterminated cable in half, and now we should see twice as wide standing waves. Now, we're getting really close. If you look at this cable, that's just 2 feet of cable. Let's cut that in half again, Ron. Let's make it 1 foot. Now, that is 1 foot worth of reflection causing that standing wave that has, I don't know, it's about 200 megahertz. That's about a 400 megahertz lambda between the nodes on it. 400 megahertz. Now, let's cut it to about 6 inches long. Okay. Point was just made. What's the difference between a standing wave and a suck out? One and the same. So you're looking at what we just created a suck out, which is actually just a half of the period of a standing wave. So whenever you see a suck out, you basically know that you have a standing wave that is caused by a reflection.
It's got a really short,
very short time delay. That is probably, somewhere between 7 inches or less in general. Once you cut that wave in half, let's go. Okay, and now you're going to see what happened. Well, we actually see that.
we probably got some braid
Yeah,
out.
there's a little short circuit in there too, so there's a kind of a compound issue. And
Probably
here,
some braid up.
that's interesting. Now, see, there you can see the frequency component of that suck out is affected because there's this conception that people have that there's a relationship to the start of the standing wave and the length of the impedance cable is just not correct. Cut that one in half. Let's go down to 1 inch. There. So the suck out didn't go away. It's just no longer in a place off the screen. It's just off the screen, right? So that's one of the interesting things about suck outs. It's actually, let me see if I can interfere with it. Can you cut that again down in half, just like a half? No, it's actually getting better now.
Yeah, because we're getting down now where we're seeing essentially the teeth.
Yeah, it's actually, if we just go ahead and remove the connector, it's indistinguishable, just got a little bit better. So anyway, the point of this whole exercise was to demonstrate microflections, how they standing the amplitude ripple caused by standing waves and the relationship to a suck out. So maybe we just give you I just ripped treble frequencies. Yes, exactly. Well said. So any quick comments? Anybody left? Did you get that whole suck out and standing wave presentation and demo? Did you? Is that a big surprise or no in the chat window? You knew that was going to happen, right?
a lot of people surprisingly are like, wow, I've never really thought of that. Like, it's a very short duration study. So. Okay, folks, we are at exactly time, and there's a whole bunch of bumps and bruises here, and I will return to in person last Thursday, but we really appreciate everybody sticking it out with us. We're having a great time here in person. Hopefully the next time, yes. Thanks you all. Hopefully next time we'll start to see you all in person and have snacks and crack jokes again in the future. Really appreciate you coming out. So with that, we'll get taken off.